everyone. So when I named this talk, I asked my mom what to call it, and she thought of this pun, and then she immediately laughed so hard at her own pun. There was no chance I was going to call it anything else. And I'm a little disappointed that there haven't been more puns this week, because I thought that we were a punny community. And that's my challenge for future FRB meetings, come up with more puns. So I'll be talking about GREENBURST, and I'll explain that on the next slide. But here are the people of GREENBURST. You've seen 2/3 of these people this week so far. And I want to thank all of them for doing this work and helping me do this work. And also, I'll shout out a couple of them specifically in the talk. Now, I hear you all asking, what is GREENBURST? Well, the motivation behind GREENBURST is, as we've heard today, as we've heard for the past 2 days, it's hard to get telescope time. Essentially, you either have to build your own telescope, if you're Canadian, or you have to have a lot of money to use a telescope, if you're not Canadian. And both of those are expensive. So what if we could really cheaply get a bunch of telescope time? And we can, by taking other people's telescope time and using it in addition to them. So, GREENBURST is a commensal experiment. It's been running on the Green Bank telescope for about 5 years. And any time the L-band array feed is getting data, we're in there, we're looking. So we have over 22,000 hours of time on the sky. And we are running all of that data through the pipeline that Graham so helpfully explained to you 2 talks ago, and now I don't have to tell you anything about. We're running it through that pipeline to find single pulse candidates. So we have over 16,000 pulsar single pulse candidates. I will talk about those briefly. We have over 14,000 uncategorized single pulse candidates. Unfortunately, I have to tell you, most of those are RFI. But we have 3 new sources. We also have a website made by Sloan, and it's currently at greenburst3.github.io, but at some point we'll move to greenburstwbu@github.io. So stay tuned for that. And the existing publications I've listed here, they're also on the website with links. Okay, so I recognize this is a really big table. Dunk said I needed to include it. You don't have to read it if you don't want to. But if you're interested, it will be in Kanya et al. In prep. So these are our 16,000 candidate pulsar pulses from existing pulsars. We've got 4 pulsars with over 1,000 pulses. They're mostly Bs because the easiest pulsars to find in single pulses are bright canonical pulsars, otherwise known as the ones that were found first. So we've got these pulsars. We do have some MSP single pulses from mostly 1937, which Shaway is also on the team, is analyzing. We've got single pulses from the A pulsar in the double system. We're not here to talk about pulsars though, but I will talk just briefly about some more pulsars. These are examples of what our pulsar single pulse candidates look like. The RFI is not great, but the signal noise is good enough that you can still see signal, even in that one. We did find a new pulsar. This is pulsar J0039 plus 5407. It was found June 9th. Well, it was observed June 9th, 2022 by GREENBURST. It was found by a human being on a date after that I don't know and can't disclose. But it's a pretty good initial detection. Signal to noise of about 15. The dispersion measure of 74 parsecs per cubic centimeter. And then it was subsequently timed with CHIME. We have an MOU with CHIME. Hopefully everybody who knows what an MOU means has no further questions. So these are the current pulsar parameters, and this is also in Kanya et al. In prep. So look for that in the next year. Hopefully much less than 1 year. But I'm not actually writing that paper, so I don't have enough control over it. So pulsars, but now we're all here for FRBs, and so here's our first one. This is pulsar, nope. This is FRB 2022-07-18A, found on July the 18th, 2022 by the telescope, by the humans in 2023. So it's at these coordinates. The dispersion measure is 145.5, which puts it at a z of about 0.07. And then we looked on, I believe, NED, but also several other optical databases, and there's no obvious counterparts in the GBT beam at this pointing, which is a real conundrum. I don't have the solution to that conundrum. If anybody has ideas, we're open. So we haven't done our own optical follow-up yet. We don't have telescope time for that, but hopefully we will. So this is FRB 2022. Now, this summer we got a little bit bored of looking at what everybody else wanted to look at, and we were like, what if we got to pick what we looked at for a little bit? So we did an elliptical galaxy survey. We looked at these 5 galaxies in a local universe for the best chance of multi-wavelength detection. All these galaxies fit in the GBT beam. They are theoretically predicted to have high numbers of FRBs per hour, which you can see the rates here. This lovely table I made. Now, looking at the time on source, you may notice that one of these has been looked at a lot more than the other 4, and you'll learn why in a second. Oh my gosh, I'm going so fast. There'll be so much time for questions. Okay, we're not optical astronomers, but it's always nice to look at a pretty picture of a galaxy every day, and here's 4. So most of them just sort of featureless elliptical blobs. So fun, so exciting. Sombrero is actually pretty cool, and it's technically not an elliptical galaxy, but you'll have to let us have this one. It's an edge-on spiral. Now, you'll notice there are 5 galaxies on the previous slide, and there's only 4 here. And that's because there's a special galaxy. This is M49. It's also a featureless blob. So it is the most luminous member of the Virgo cluster, and it has, according to NASA, almost 6,000 globular cluster stars. This is an old galaxy. It's got a lot of globular clusters, and this is a real weird thing, considering what we found here. Its apparent magnitude is 9.4, and what that means to me is if I was at my undergrad telescope in downtown St. Paul, Minnesota, you could see this galaxy. Just barely, but you can see it, so it's pretty bright. And we found an FRB from it. This is FRB 2024-0817, and it was found by humans and the telescope on the same day. The human was me. So it's a beautiful, beautiful burst. If you ignore all the weirdness, but that's a DM peak. There's a frequency line there. I can see it really well. Hopefully you can see it too. And it looks gorgeous. So it's from the direction of M49. We say that because the dispersion measure is quite high, 983, which means it's almost definitely not actually from M49. M49, very old galaxy, theoretically doesn't have a high gas content and is making a small contribution to the DM. But there could be something weird going on. Once again, not an optical astronomer. Maybe there's something crazy going on there. The width is 8 milliseconds, which is pretty typical of green-burst bursts. This is, I'm not kidding, this is the best FRB detection. Our signal to noises are generally quite low. I should put what this signal to noise is. I can look that up later if you really want to know. So this is our beautiful, beautiful FRB. We detected it in the real-time green burst pipeline, and then I reran the data and I detected it again, so that's great. We also have, since we were the official GBT observer, we have Vegas observations of this time. So we have full stokes, which is exciting and excellent. What we don't have is computer space. So we have not processed all of this data yet because there's been nowhere to put it. But there is now somewhere to put it because Joe Glazer and WU connected like 100 new terabytes for GREENBURST last weekend. So, before FRB 2025, I will have processed that data. And that's a promise, and if any of you are here, you can hold me to it. Then, we also hope to do a spiral galaxy survey with GBT, hopefully before the end of my PhD, so that puts us in the next 2 years. We also want to replicate this kind of work with FAST. FAST is even better than the GBT, larger field of view, greater sensitivity, so you need less time to get the similar limits from FAST. And there will be a paper about all of this forthcoming, but it's not even in prep yet. But it will happen before I graduate, at least. And this is my last slide, and that took me 11 minutes, which is excellent. And now I'm done.
We have answer questions.
So I had 2 questions. The first was about the first FRB you detected.
Yes.
There were some dash lines on the waterfall that kind of looked like maybe there's a period.
Yes. So, those are for the period. This is a very bright pulse, but our hypothesis is this is a period. We have followed up this FRB and found nothing else. And we searched every other time that the Green Bank was looking at this spot and not found anything. So it does appear to have periodicity, but it's not repeating constantly, which is expected. If you want more periodicity, I'm pretty sure it's in Joseph Coney's thesis, which is linked on the GREENBURST website.
And the other quick question I had was for the second detection.
Yes.
Maybe I missed it, but do you have polarization data for that?
We do. We have Vegas data. We have not looked at the polarization yet, but that is also an immediate next step. So GREENBURST itself doesn't take polarization data. That's too much data. But because this was during this galaxy survey, we have Vegas data of this exact observation, and I will, once I learn how, be looking through that.
So we have some models for M49 about the distribution of matter. Can you put an upper limit of what's the dispersion measure if you go through, and therefore try to extract what's going to be the range of redshifts that these FRBs have?
Yes, we can do that. We haven't done it yet, but we can do it. So I don't have numbers. If you're looking for numbers, I don't have them, but it is theoretically possible.
Yeah, because you said this dispersion measure is too high to be from M49.
Yes.
What's the maximum dispersion measure that you could get if you go through?
My remembrance is like about 500, but really don't quote me on that. So it is, I believe it's about twice as high as we would expect from M49. Once again, though, it could be just through a very gas-rich part of M49, which would increase the DM. I don't know that the resolution of like the H1 content of M49 is high enough to determine like a specific cyclone might have more or less.
I think it's a good thing to say.
So on a similar sort of note, do you have any plans to follow up to look for like persistent radio sources or persistent radio sources associated with this course?
I think that is the thing we're going to look at our Vegas data for. We would love to do more follow-up. So this was found in our third observing session of 7 or 8. No, it's 7, but there's no session 5. So it's 8. It goes to 8. There's only 7. So that's why we have 10 plus hours. So we're hoping that the follow-up after we found the burst might have something in there. Great. Would be a good proposal.